Wait another couple of seconds. Okay, now we waited a minute, so I can stop sharing. Everybody knows that they are in the right webinar, and we can start. Okay, so good afternoon, everyone. Welcome to this Monday afternoon NITheP colloquium. It is my great pleasure today to introduce to you today's speaker, who is Sir Peter Knight, and he's joining us not from Imperial College because of the COVID situation, but 70 kilometers north of London. Yeah, and I'm really very happy that Sir Peter is with us today because, as you know, we are also working on our local South African roadmap and framework for quantum computing and quantum technology. So it will be very useful to hear from Peter how the trajectory to a really working and efficient quantum technology program worked out in the UK. Before I ask Peter to start with his presentation, let me briefly give you an idea of his biography. First of all, he will probably be known to most of you. At the moment, he's a senior research investigator at Imperial College, because a few years ago he retired from the position of Deputy Rector Research from Imperial College, and it's still a Professor Emeritus at Imperial College. Yeah? In 2005, he was knighted because of his contribution to quantum optics and maybe optical physics in general. In the past, he's been president of the Optical Society of America, and he's also past president of the UK Institute of Physics. He's the editor of a very nice journal that I like very much, Contemporary Physics. And importantly for us, he's the chair of the UK National Quantum Technology Program Strategy Advisory Board, and is also chair of many other UK institutions, among which also the UK Defence Scientific Advisory Council, and he's still a science advisor to the UK government. Over the years, he won many prizes that I won't list now here singularly, but essentially most of the prizes that you can get, Sir Peter received over the years. So we are really privileged to have him here this afternoon with us. So Peter, sorry, before I ask you maybe while I ask you to start sharing the screen for your presentation, I will briefly introduce Dr. Sinaisky, who kindly agreed to moderate the answer and question session after the talk. So please make use of the Q&A facility at the bottom of your screen. And after the talk, Dr. Sinaisky will moderate the questions for Sir Peter. Yeah, Peter, please, the show is all yours.
Thank you, Francesco. It's a great pleasure to be talking to you all. This is one of the rare years when I've not been to South Africa. I've been involved for quite a long time in discussions and collaborations with NITheP and others. And so these COVID days mean we have these virtual presences instead. Instead of giving a very technical talk today, what I'm going to be talking about is how we put together a quantum technology program in the UK, which brought in quite a lot of partners to build an ecosystem by which we all collaborated together. So there's quite a lot of policy stuff in here, but I'm going to be talking about what are the opportunities in the quantum space that enabled us to put this program together and who the partners are. And when we started, we had a number of collaborators, and on this first slide, in fact, they're all named there, and I'm going to run through them bit by bit. So the government department that provides a lot of the research support is called BEIS, Department for Business, Energy, Innovation and Skills. The Research Council, EPSRC, our translation agency that works with industry called Innovate UK, the Knowledge Transfer Network to build up networks, DSTL, which is the Science and Technology Laboratory of the Ministry of Defence in the UK, the National Physical Laboratory, which is our Metrology Institute on standards. Whoops, we've jumped one too soon. And the National Cybersecurity Centre, who are advising us on a whole raft of security issues relating especially to things like quantum communication and in quantum computing. Right, so it's quite a multifaceted operation. And I think whenever I speak about quantum technology, that to those who don't work in it, they think I'm going to be immediately talking about quantum computing. And certainly that will be an element of it. But in this diagram here on this slide, what we tried to do is to indicate the range of things that quantum will have an impact on in terms of new capabilities. And so on the left-hand side, things that are relatively immediate, and on the right-hand side, things that are very much more long-term. But the journey from left to right generates capabilities that are useful. And so, I must stop doing that. So, for example, clocks, more and more immediate, quantum communication, sensing, communication side of things are more immediate. And the timing that's on this funnel diagram was from when we really started 6 years ago. And the timescale that we estimated in each of these areas has been approximately right. Quantum computing, of course, is the one that attracts a huge amount of attention. And what I'm going to be doing is explaining how it is that there's a completely different paradigm in quantum computing. So I put a little note to myself on this slide saying the power of 2 to the n. That's to remind me to say something. Okay, right. So let's have a look. Why quantum in the UK? Well, firstly, it really is a disruptive technology. There are many things that one can exploit using quantum physics, which are disruptive of existing markets, but also offer new markets. The global cybersecurity market is already predicted to have the most enormous impact on the economy. Quite good estimates are talking about 164 billion pounds by next year. The global GPS navigation system currently is worth, in the UK alone, 21 billion pounds in terms of its contribution to the economy. And part of the delivery mechanism by which you actually get things to happen is industry, of course. And one of the great success stories in UK industry is the photonics industry. It grows at never less than about 8% per annum. It's currently worth about 10.5 billion, and it's a big UK supply chain success. Of course, it's relatively invisible because it's under the hood, as it were. It contributes to many, many things. And so what I'm going to be talking about is instrumentation, and the little pictures there are, for example, a gravity sensor and a clock, which can be really seen to be the kind of transformative things that really could disrupt existing markets and offer new markets. So we talk quite a lot about the quantum age, and it's really important to remember that we're living in the quantum age anyway, because of course we have lasers and semiconductors and all the things that quantum physics allowed us to build, starting with the great discoveries in the 1920s, really transformed industry and the economy. What we're talking about now is exploiting this new feature of quantum mechanics that we've only recently been able to manipulate and control, and that's quantum coherence. And it impacts many, many sectors. And it gives us new capabilities in timing, in sensing, in imaging, computing, comms, and so on. And so what I'm going to be showing you is some examples of where it makes that an impact in those various areas. And in the little box, I've got various pictures of component parts that play a role in this, from chip-based systems, photonic systems, and so on. So let's have a look at how we started. Since about the 1990s, we've worked out really how to control, in particular, things like single quantum systems, to exploit superposition and entanglement. These rather philosophical things that used to dominate academic discussion had the potential for exploitation that was really recognized at the end of the 1990s. We started a program really to try to do that exploitation in the UK about 5 years before other people did. And we think that we could see game changers in sensors, in comms, and in computing. And so in order to get this underway, we produced a vision piece which was successful in persuading government to commit substantial resource. So in the autumn statement, the budget statement, if you like, in 2013, the then Chancellor of the Exchequer, there he is, George Osborne, at the time, set aside 270 million of new money. So it wasn't taken away from other parts of the science budget. So new money that contributed to the formation of this new program. And that resource, 270 million, was something that we had a 5-year vision to exploit this, a range of technologies, but the purpose being to really create new economic opportunities, to create new jobs, to create UK wealth. That program, which started, as I mentioned, over 6 years ago now, is running at about £1 billion over a 10-year period. And I'll talk about that journey. So in order to get this thing to work and to really make an impact in the economy, you need an alliance of the actors in this space. Academia, because that's where scientific knowledge and future breakthroughs stem from quite often. Industry, although they also generate new technical ideas, but they certainly identify markets and opportunities. And government, which not only pay for some of the research activity, but often can act through the early adoption of product as an accelerator in this. And of course, the overlap in this quantum alliance requires coordination. We need to cluster skills. We need to worry about standards if this thing is going to work in a global way. So that's the quantum alliance. All of those partners have to be brought on board with a shared common vision for this. So what we did is that we set up research hubs, and I'll explain those as we go along. Those research hubs focused on sensing and timing, on quantum secure communication, on quantum computing, and on imaging. Now, if you look at the examples I put here, these are all things that emerge from that science. For example, compact atomic clocks for time stamping and so on. So we set up those research hubs, 4 headquarters. Those headquarters were in Birmingham for sensors, in imaging in Glasgow, in quantum communication headquarters in York, and in quantum information processing at Oxford. But those 4 headquarters also engage with 30 universities. So it really was a complex ecosystem that everybody played a role in. In addition, we had resource which grew called the Industrial Strategy Challenge Fund, where we produced challenges in these areas for joint work with industry producing matching fund as a way of accelerating that translation activity. So we're not alone in working on this around the world. This is a fairly hourly snapshot of what was going on around the world. What can I pick on this one? In Canada, extremely strong quantum program. This is the Prime Minister of Canada, apparently explaining what entanglement does, which was most impressive at the time. In the United States, the National Quantum Initiative signed off by the White House to generate a major program. In Europe, the European Union have a flagship program. We've got our own program, of course. In Australia, in New South Wales and in Brisbane, 2 centers of excellence in this sort of area. And of course, in China, and I put one of the visionaries there, Jianwei Pan, and the MESIA satellite has been transformative. So a lot of work going on worldwide. We're not alone. And about 5 years ago, in a special issue of The Economist magazine, we worked with McKinsey to get some sort of breakdown on the annual spend in millions of euros around the world. And this is what you saw from that McKinsey report for us. And you can see the big player there, the United States, Germany being another big player, China, a really big player. There's the UK. Okay. That's what it looked like 5 years ago. What does it look like now? Well, of course, you have to distinguish resource that's committed from resource that you may have an aspiration to spend. But what it looks like now looks like this: a huge expansion in the US activity and a huge expansion which is planned for China. So the worldwide spend is really, really substantial. Having got this initiative off the ground, what we then did is that we thought we ought to be looking at the opportunity space that this new technology provided. So working with the then government chief scientist, Mark Walpert, Mark and I wrote this document called The Quantum Age, which was meant to be for policymakers, not for techies, but to try to explain what quantum technology might do, how disruptive could it be, what are the new opportunities, and it gave a set of recommendations to accelerate our activity in this area. As a result of that review, which was an official Government Office of Science review, we saw a very major expansion in the resources. Now, I mentioned the 270 million in 2013 commitment. The spend started in 2014. That was our first phase, phase one of that program. And it grew to over 400 million by its end in 2019. We put together these hubs that I mentioned, skills programs, industry support. Phase two, a second 5-year program, started in the autumn, in the European autumn of 2019, with additional commitment. And what this pie chart shows you is how that 1 billion program, the 10-year, the 2 5-year programs, is put together. And you can see the largest single component part now of our national program is collaboration with industry. That industry partnership amounts to 45% of that 1 billion. The hubs got refreshed. We acquired new skills as new people emerged, new hires were made, new groups were formed, and we brought them on board and we refreshed those hubs. In addition, we built something called the Quantum Metrology Institute at NPL, looking at standards, verification, and validation. And in fact, I chair the Quantum Metrology Institute at NPL. Other programs or other government departments looking at the way that they would procure prototypes for this program that I'm going to explain as we go along. And then the final part of that slab is labeled NQCC, and that's the National Quantum Computing Centre. And that was about £100 million of startup money to build a national centre on the Harwell campus near Oxford, to really look at the way that some of our more interesting quantum information processing architectures could begin to scale. So that's the 1 billion program. We haven't neglected international collaboration. We have a funded collaboration with Singapore on using a CubeSat for a quantum communication experiment between the UK and Singapore. We're about to announce, I think probably on Friday, a formal funded collaboration with Canada. And we're looking at collaboration with Australia and other countries as well, for which we have common interests. So how are we going to get this stuff to work? How do we make these material things quantum correlated, which is one of the things that we need to exploit these new potentialities? And they certainly need to be cold. And the way we do it, for the most part, is using laser cooling. It's not the only way. There are cryogenic experiments that just require extremely sophisticated dilution refrigerators, but usually it's laser cooling. And just to run through how laser cooling works, it's a little bit like slowing up a bus by throwing snowballs at it. You know, eventually you will slow down the momentum of an atom. And in fact, so much so that you can reduce the temperature of atoms to a tiny fraction above absolute zero. Now, as you do so, what happens is the atomic properties start to exhibit these quantum mechanical wave-like properties. They become like matter waves. Those matter waves eventually end up, if you are really careful about it, with a thing called a Bose-condensate. And that really is a matter wave, like a laser light wave, but made of atoms. And they interfere, just like light beams interfere. And if you can figure these cold atoms above a substrate, you can measure rotation, gravity, acceleration, and many other things. That's the kind of thing, the component part of the basic science program that we also fund, that leads to these new technical capabilities. And at that point, I should say that as well as our quantum technology program, 10 years, 1 billion, we also support fundamental science that's underneath it all, because without that, you don't have a pipeline of new insights. Right, so quantum sensors. What are we trying to do with quantum sensors? Well, we're trying to build a navigator, for example. How do you measure acceleration, rotation, and so on? And what do you need for that? Well, it'd be good to have a quantum chip that will do this with cold atoms, to build magnetometers that measure magnetic fields. Some of the sensors have the capability of imaging through walls, as I'll explain in a moment. You can do many other things, but in particular, you can start to sense gravity. And that's really important for things like oil and gas and mineral work, but also it's important for defense. Are your troops working along a road that may have an IED under the road, for example? You can sense the change in the gravitational field. You can also sense electromagnetic fields, and there's this rather surreal picture on the bottom right-hand side is a brain image, a functional brain imaging helmet. And what that is doing, it's using little quantum magnetometers embedded in a helmet-like structure to read out the electromagnetic environment as the brain starts to work. Now, prior to this, you would need either a very large superconducting tunnel in which to insert people, or you need brain surgery, in fact. This is non-invasive, it's like a cycle helmet, and it's already being road tested on real patients for their diagnosis of a number of things, including epilepsy. So huge changes in healthcare coming about from this. These are simpler in terms of their infrastructure requirements and can be run in a hospital, and they are being run in a hospital already as a test. Now, how about timing? And we've had a long history. This is a double log plot of the way that clocks have evolved. Sundials on the top, then pendulum clocks, quartz clocks, then the big fountain clocks, which at the moment are the way that we define the second around the world. And then there are newer clocks, and some of the newer clocks are more accurate than the standard, which means we really have to move towards a new standard. So fractional accuracy has really hugely improved. And there are many reasons why we need that increase in fractional accuracy. But what we also need is things without that fantastic accuracy, which are compact, resilient, and can be transported. Now let's have a look at that. You all use atomic clocks just to navigate. Your GPS system is driven by atomic clocks. You look at satellites. There's an elegant way of looking at the time of delivery of the coded signal, and from that you can work out exactly what your position is. Now think about GPS or GNSS in general, is that it's extremely vulnerable. It's easy to spoof, it's easy to jam. And so we need a resilient structure that could actually technically replace it if, for one reason or another, GPS goes down for a while. And that's one of the things that we're actually pursuing here in the UK. And one of the triggers for persuading governments that this is worth investing in as a field was a thing called the flash crash. and this is not really a physics problem at all. What this was a very dramatic change in the stock market value in New York on May the 6th, 2010, caused by automatic trades, where about 650 billion pounds evaporated from the US equity market, really just for minutes. There was a bit of hysteresis, didn't all come back. And at the time, our government really got quite alarmed by this. I sit on a government advisory panel, which was asked, how do we stop automatic trades? And we said, no, you won't, because these traders are looking at ways of reducing the latency. What we need to better do is to timestamp everything in the network. And that way, if you timestamp, what you can do is throughout the network, every switch, router, server, processor, all the rest of it has to be timestamped so that you know who did what in what order. Otherwise, you might feel that trades occurred before they'd actually been executed. So synchronization of networks is the way that we need to be able to produce subsidiary clocks that get embedded in the network and distribute timing in a resilient way. And it has to be traceable to UTC, Universal Coordinated Time. And we need to do it in certainly the order of tens of nanoseconds. And it gives us a resilience against either a malicious or an inadvertent downing of GNSS. Let me turn to something else now, which is another feature of quantum technologies. You see laser ranging everywhere. Time taken for a laser pulse to get from you to an object and then come back, it gives you the distance. But what you can do that's new in quantum technology is to use pairs of quanta, pairs of photons. They're born together as twins. One of them you can use yourself as a kind of trigger, and that alerts you to the fact that the second one is on its way. It goes off on its journey to a target, comes back again. And because it's so closely correlated with the one that you had as the trigger, you can do a whole load of ranging. You can do it covertly, you can see around corners with this thing, and all sorts of fun applications. So I thought I'd show you one of the ones. There we go. This is how it all works. You have blue photons, high energy ultraviolet blue photons. They're produced. They go through a nonlinear crystal that's held on that mount. And that nonlinear crystal converts them into twins, pairs of lower energy photons, either in the visible or in the infrared. Conversion efficiency is terrible, actually, but it doesn't really matter. You get these correlated twins. What can you do with them? Well, one of the fun things is you can do ghost imaging. So on the left, here's my ultraviolet photons coming in. There's my nonlinear crystal. It makes these twins, okay? This one, say, in the infrared. This one in the visible. Infrared is really, really hard to detect in any specific way. Visible is dead easy. Lots and lots of detectors for visible. So what we're going to do is image this object. Okay, you have a bucket detector. These photons are born as twins, in pairs, correlated. One goes there, gets disrupted by the object. This one goes there, bing, 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 to a camera back. And you do a coincidence experiment between the two. So you get over here an image in easily detectable visible light of an object that the visible light never saw. It's the infrared that saw the object, but because they're correlated, what happens to that one is mirrored by this one. The correlations are there, and you make the image. Now, of course, you can actually do that as long as the light's correlated. You can do it classically correlated, but quantum gives you an extra advantage. That's called ghost imaging. It's great fun, and it has practical applications. What about secure communication? Well, how would you communicate anyway in a secure way? The way that one normally would do it is you've got a sender, let's call them Alice over here, unprotected data. And what you do is you've got a cryptographic key, which is secret, and some transformation, which you could declare. And you combine the secret key with unprotected data, and now that protected data goes through the hostile network to a legal receiver, Bob. Now, someone is trying to tamper with that network, an eavesdropper doesn't have that key. Make guesses if you like, but unlikely to work, and certainly will not be able to work without revealing themselves. But Bob has a copy of that secret key and can invert that mathematical transformation and get the plain text, the unprotected data back in a secure way. And that's the traditional way in which one would ensure communication. And I'll come to say why it is that quantum is going to play a role. So the fact that quantum makes a difference in the way you process information has a kind of history of heroes. One of our heroes, of course, is Richard Feynman, top left. And he noted very early that quantum systems are really hard to simulate on a classical machine. You run out of memory, you run out of state space. And he did propose that perhaps the best way to simulate a quantum system is to use another quantum system, because the state spaces will be similar. David Deutsch in the middle from Oxford noted quite quickly after the Feynman proposition that a machine using quantum mechanics can perform calculations that might be either very hard or impossible for a classical machine to perform. And of course, the famous example is Peter Shor's factoring algorithm. Factoring is hard classically, but it becomes easy with a quantum computer. And that really started to transform people's view of the world. Really, a lot of quantum computing started as soon as Peter Shor published his quantum Fourier transform algorithm. To demonstrate how that works, this is a large number, RSA 2000. RSA is the system which leads to the security of our internet. It's the basis of TLS and HTTPS and so on. Keep doing that, sorry. And that has factors. They're the prime factors of RSA 200. Now, to factor that number into these two prime factors is really, really hard. It uses a lot of instructions. It takes a long time, even using the best algorithms. To check you've got it right is dead easy, because that's multiplication, and that's just polynomial. Okay, so to break an RSA crypto system is really hard. It requires exponential work. Okay, but to use it only requires polynomial work. As soon as Peter Shor's algorithm came along, our defenses were blown, because classically, because it's exponential, all you had to do is increase the key length. Instead of using RSA 200, go to RSA 1000 or more. And that would take hugely longer to break. But the quantum machine, using Shor's algorithm, does it polynomially and will break RSA once you have such a machine very quickly. So there you go. That's the challenge. So do we need to worry about it now? Because we don't have a quantum computer yet of substance that you could break RSA. On the other hand, how long will it take? And this I've taken from my colleague Michele Mosca in Waterloo in Canada. And it's a very succinct way of demonstrating how you need to plan resource allocation over a long period to secure one's infrastructure. And we do need these cryptographic keys, otherwise you cannot do anything on the internet safely. So how long do you need your key to be secure? That's your shelf life, let's call it X. How long does it take to retool the existing structure with something that's going to be quantum safe? You know, in other words, immune to a quantum attack. Let's call that Y. That's your migration time. And then make a best estimate of how long it would take for a large-scale quantum machine to be built. Let's call that Z. And the Mosca theorem is that if x plus y is greater than z, then you worry. In fact, not only do you worry, you panic, because it'll undermine everything you knew about the security of your national infrastructure. Okay, so now we need to estimate how long these timescales are. I'll jump ahead. The very best estimate for a large-scale machine at the moment is coming down. I used to say it's quite distant. If I said 10 years, how long does it take to retool the existing infrastructure, quantum safe? It's about 10 years. When do you start working on this stuff? Now. Okay, everybody around the world needs to be alert to this. Right. So there you go. Best estimates from Michele Mosca in Waterloo that was presented 3 years ago at the ETSI workshop. Large-scale quantum computing is 10 to 15 years away. A 1 in 7 chance of crypto primitives affected by quantum attacks by 2026. A 1 in 2 chance by 2031. Those estimates have come down very substantially. We need to be even more alert now. Right, so quantum security. There are a number of ways in which you can generate quantum security. One is to share random numbers. You generate something like a one-time pad. Now, classical physics isn't random, so quantum could be. But the problem is to be able to know whether a bit string is actually random. I can't resist this Dilbert cartoon of the random number generator. He says 99999. And of course, that could be a part of a random string. You might have to wait a bit longer to work out what the entropy is. So knowing whether something is random is really important. And it's that randomness which underpins so much of what we might want to be able to generate. So if we want to make quantum safe cryptographic toolboxes, there are numbers of things you can do. You can start worrying about random number generators that really are random, that are shared and shared safely and secretly. And there are quantum optical ways of doing that with beam splitters and so on. Or you could build quantum post-quantum algorithms, quantum resistant algorithms. They could be some lattice vector sort of hash-based systems for which there is no safety proof. They're just thought to be safe. Or you can use quantum key distribution, where you use the laws of quantum mechanics in a different way. Right, so here's how an eavesdropper always reveals themselves in a quantum system. So if Alice is sending strings of quanta, photons, from Alice to Bob through a hostile network, the eavesdropper intervenes. And the point about an intervention or a measurement in a quantum system is that the measurement disturbs the system and therefore reveals the intervention so that you can detect an eavesdropper. So what you can do is build a cryptographic protocol which could be secure, but only if it's operated securely. You know, if you have a lousy hardware security on it, there are always ways of getting into the system and controlling it. So my colleagues at GCHQ will always say, security is the security of the entire system, not of the component bits. Right. So what have we done in the UK? In this, we've built a QKD network between the British Telecom laboratories over in the east of England at an Astral Park, through installed fibre, through the telephone exchanges to Cambridge University to run secure video between the two sites, and road testing, looking at the security of it, looking at vulnerabilities and so on. That's an example of a short distance QKD network with trusted nodes. Now let's look at a really big one. Here's a really big one between Beijing, Hefei, and Shanghai. Now that really is an enormous, it's 2,000 kilometers. It's got 32 relay nodes and so on. And these nodes have to be trusted nodes. You have to run those nodes yourself. Until we get quantum repeaters, we can't guarantee the security. But certainly they have banks that are running tests on this thing already. We don't need to run it through fiber. And a huge success stemming from the launch of a satellite called Mesius was a satellite communication between China, a satellite, and back down again. The satellite acts as your trusted node to transport the key, and you can do that over huge distances. And the Mesius satellite really demonstrated that. And here we see a quantum key secured video conference between Zhang Weipan in Beijing and Anton Zeilinger, one of the doyens of the field, in Vienna. Okay, so that's a satellite protocol for this. Now let me turn to quantum computation. And physicists like these heretical statements that computation is a physical process. That does tend to offend computer scientists who think of it as an abstract computational process, but it's not. The hardware obeys the laws of physics. So what would a quantum computer look like? And I can't resist this quote that many of you may have seen from me already. Computers of the future may weigh no more than 1.5 tons. I'm going to show you some 1.5 ton type processors from quantum, but that was from Popular Mechanics in 1949. Things move on. Okay, so the basic idea of quantum computing is to use superpositions. These superpositions allow you to grow your state space exponentially. So if you have n qubits, you have 2 to the n states that you can start to access. There are growing numbers of algorithms that can be deployed to exploit this 2 to the n state space. And they're listed very nicely in this website that I've demonstrated here called the Quantum Algorithm Zoo. There are many, many algorithms that have been proposed, road tested, and so on. So here's one that I picked out. And of course, it's the factoring algorithm of Peter Shaw. This is extremely techy, but what it demonstrates is that even the very best classical algorithm for factoring to find the prime factors of a large number is the number field sieve, and it takes a very long time to run. Whereas a quantum algorithm using a quantum Fourier transform does so polynomially. So what it means is that RSA or versions of RSA, and in fact even elliptic curve protocols are broken. And the key exchange protocol called Diffie-Hellman is broken as well. So there we go. Lots of algorithms. This slide also mentions Grover's search algorithm. Grover's search algorithm also can be utilized to look at elliptic curve methods for encryption. So we need to find algorithms that are quantum safe, and we need to explore quantum key distribution and make sure that the whole system has a provably secure space. Right, so we have a quantum opportunity if we can build one of these machines. We have a roadmap for building a quantum computer. We're fairly well positioned to deliver hardware, software, and applications. So there's lots of examples on this slide: trapped ions, superconducting, and so on. So let's have a look at what we can do. In 1996, a couple of years after the Shaw initial paper, there was a great chasm between what experimentalists could deliver and what theorists were demanding to run a non-trivial algorithm. Experimentalists were generating 10% errors in their bits. Theorists were demanding much, much less error. And so there was a kind of game of working out how long it would take to close that gap. No one really knew, but many people guessed. Some people said a few years, some people said many decades. Some skeptics said it's not going to be possible. We never close the gap. You will always make too many errors. The reality is you close that gap in 20 years. The experimentalists got better and better at controlling their systems. The theorists found better and better algorithms that were less demanding. The gap is closed. There is no chasm now. It's an engineering challenge to scale, but the physics of this, we now have a way forward. So what approaches can you take in terms of technologies? Trapped laser-cooled ions, superconducting qubits, nitrogen vacancy centers in diamond. You can use a photonic platform, silicon spins, topological qubits. And on the left-hand side, a lot of the majors are playing to their strengths in this space, really investing. On the right-hand side, there are lots and lots of research institutes set up to address these kinds of issues. Right, so what to do to bridge this chasm? We're pretty close to here now, 50 qubits, probably 100 fairly soon. And that means you've got what's called a noisy intermediate scale quantum computer. And with that kind of scale, you've got 2 to the n, so 2 to the 50 is already a really huge number. And that's where Google had their famous quantum supremacy result from last year. But we've got to be able to repair errors to do something substantial. And that's still quite a journey that's underway, people with ideas. So startups are starting to look into this space as well as the majors. So we have majors, Intel, IBM, Google, and Rigetti, all putting resource into this. In terms of photonic platforms, Xanadu and PsiQuantum, which half came out of Bristol and half out of my own group at Imperial, looking at photonic platform. IonQ in the United States from Chris Monroe and company, and there's one in the UK as well. And then the spin systems that Michelle Simmons in Australia has been pursuing, for example. So what we've done is to say, well, we have these hubs that are looking at the research potential of various vehicles for quantum computing, but now we needed to do something about pulling the best of those, the most promising, into studies of how you would engineer scale up. So that's where we've invested 93 million over 5 years to build this National Quantum Computing Centre at Harwell. So there's a kind of artist's impression of what the building is like. The construction started. We've hired a team. We're focusing initially on superconducting qubits and trapped ions to build an SQ machine quite quickly in the UK. So the launch has already happened in September of this year, and we're in the middle of hires. So let me go to the hubs. So we have this sensors metrology timing hub. It is based in Birmingham, but it's got universities all over the place. You can see them, including Imperial College there. Excellent. There are 110 collaborative projects or more. A lot of companies have been investing. And the total project value is now grown to more than 120 million, in addition to the seed money that the government put in. It's created 50 jobs so far in the industry from that single hub, and so on. So really rather promising on sensing and timing. And here are some of the products that some of the component parts that they're building. And you can see an awful lot of companies are involved in this. I won't go through all the details. Okay, so accelerometers, gravimeters, clocks, gravity mapping, all sorts of things coming out of that particular hub. On our imaging hub, headquarters in Glasgow, is to look at novel imaging using quantum correlated light or quantum generated light, where you have timing, you know when the photons were born. And again, lots of universities engaged in this one. And there's been a massive investment so there's over 600 studentships that have gone into this program. Lots and lots of companies, lots of products already underway. Now, what about quantum computing and simulation? That's the hub based in Oxford that again involves lots of universities. And what they're looking at, as I mentioned earlier, is the underlying physical platforms and the algorithms and the theory of all of this that support our identification of promising platforms for the National Quantum Computing Centre to start to pursue. So work on algorithms, working on simulators, annealers, and so on. The goal eventually is to really hope that we will get a universal fault-tolerant quantum computing machine. But in the meantime, an NITheQ machine already offers great potential. Right, so they're the hub partners, lots of universities involved as partners in this. And that's the unique feature of all of these hubs, is that the universities are beginning to work together in a common enterprise. And then on the right-hand side are the industrial partners for quantum computing and simulation. And they involve the usual suspects in terms of computing, startups, big data places, but also the end users, for example, GlaxoSmithKline, in understanding how molecular structure can be understood for things like drug discovery. Okay. So quantum communication, I mentioned already their Metro Hub and so on. They've actually got a number of spin-outs that they've developed, both handheld and more than ever, they started to look at the space side of it all. Lots of engagement on standards with NPL, with Toshiba and so on. But also in big projects, Aquasec, which has produced a Metro multi delivery network in Bristol. So if you look at what they've been able to do in that hub, they built their test beds so that companies who want to be able to use these, for example, British Telecom, can really start to look at the potential for this. They're also looking beyond QKD and quantum communication at post-quantum or quantum safe, and in particular doing a lot of security analysis, testing and so on. If you're going to start talking about your system as secure, you've got to put a lot of effort into the entire system. CubeSats, of course, give us a great opportunity to road test some basic ideas about how you can use space more. So this is my final slide. This is one example, and I could have used a slide for each of the hubs to demonstrate how complex the ecosystem is that we've generated. University partners comfortably working together. We're just coming to the end of our 6th year of collaboration in a harmonious way, but we pulled in other government departments. We've pulled in a number of major players like British Telecom and Toshiba. But in addition, a lot of startup companies that have come in. Small companies like KETS, producing random number generators, as well as handheld systems. Larger companies, Teledyne E2V, who started to look at some of the component parts, especially for space. Arcit in terms of space. And that's an example of what we're trying to do in building a complex ecosystem where the great science that was underway in the universities continues, but we have a vehicle to move research out into prototypes that we can test, and then into real products that meet a need in industry and in the real world. It's been a great privilege to actually work on this, to generate this. The UK government's commitment of £1 billion to this over the 10-year period is pretty much a unique contribution. It's certainly the largest amount of resource that the UK government has ever put into a disruptive technology. But I think they fully realize that quantum technology is transformative. It will change our lives. And being prepared for that has been a great privilege. It's great fun. Some of the brightest people that I've ever met are involved in this. And it's been just a wonderful roller coaster of getting things moving in this very exciting field. So thank you for listening.
Yeah, thank you very much, Peter, for an excellent talk and a fantastic overview of the efforts in quantum technology and the successes in quantum technology and quantum computing in the UK. Ilya, are there already some questions from our participants, or can I
not
ask
yet.
a question?
Okay, there is a first question from anonymous attendee.
Okay, perfect.
Thank you for such a wonderful talk, absolutely delightful. The potential of quantum technology, of course, cannot be understated and offers a great deal of hope. However, the physics behind these technologies is difficult to understand. In your expert opinion, how do we contend with these, particularly with public distrust and on the decline?
Right, now that is a really important question. So looking at ways in which we engage with the general public, we engage with not just policy advisors, but policy makers in an intelligible way is really quite important. So each of the hubs has an outreach program, and we have a national outreach program on this. We have these people called quantum ambassadors. The quantum ambassadors really do a great job in working with the general public. We put on events at science museums around the country. We have a whole load of interactive events. One of the strangest things that I ever did was a quantum pub night in a pub in Loughborough, where the general public came in, and we gave a very simple overview talk, and then we just discussed quantum physics and the pub was packed with people sitting on the floor listening to quantum science. I think they do find quantum science a kind of both fascinating and difficult subject, because almost by definition it's outside of our everyday experience, but the general public is certainly interested. I'm not at all certain that people have a fear of quantum technology if you explain very carefully what it is that quantum technology will enable them to do in a way that will be usefully affecting their lives. And the obvious one was the healthcare example I showed very early. So engagement is important. And I think one of the things that's really important is that you don't always use old men with grey beards to do the outreach activity. Our students are our best ambassadors. One of the things that I know very well in South Africa, for example, is the student chapters of OSA and SPIE have a fantastic amount of outreach activity. And that's the sort of thing that's going on around the world, getting students engaged with this. And the ones I know of in South Africa have done a wonderful job on this one. We try to do much the same here, of getting young people out there and doing things. So I mentioned my pub night talking about quantum physics in Loughborough. But in addition, some of our young people turn up at some of the big music festivals with a kind of stand and talk about quantum science. And they have a lot of people coming along listening. People want to know. It's a very difficult subject to explain. I try to avoid things like spooky correlations and so on, because I think people start worrying about the supernatural. But making an effort to do it, you get a tremendous amount of positive feedback from people. I've given talks in my own village about quantum physics in the evening to folks as well. And it's gone down well. So get engaged. Everybody should do it.
Okay, thank you. Let me ask the next question from Martin Buchler. So thank you for the inspiring talk. I have somewhat a technical question. How does single molecule NMR work? Conventional NMR using coherence of many molecules to provide a large signal, so detection must be challenging for a single molecule. How is the signal detected?
So the single molecule stuff is really something that people are exploring using spin sensors that are down at the single molecule level. This is kind of important for people to start looking at what happens for them in the mechanism, for example, of how some sort of pharmaceutical molecule penetrates the cell membrane. Okay, so they are using all sorts of interesting spin readout systems working at the single spin level. It is complex. And the group that's doing this is working quite closely with one of our companies, in fact. So Element 6 has a research activity on NB diamond spins that has an interest in this area. Element 6, of course, again, has strongness for South Africa because it's a component part of De Beers.
Okay, so the next question is coming from the Rob Adam, and he wants to ask you, what is the plan to deal with the historic encrypted data, which is already intercepted but not decryptable with classical methods? The quantum algorithms will be deployed on this data when the hardware comes of age, revealing the kind of strange things, surely?
Yeah, no, that's a really excellent question. There is no quantum solution for that. What has happened is that the high value encrypted information could well have been intercepted and stored by a malevolent actor on the basis that one day they'll find a mechanism to get in. And there's nothing you can do to protect it. The best you can do is try to identify the value of stuff that's gone out there using RSA over the last couple of decades and triage it to work out what the consequences are of that information being known. So it's triage, basically. There is no way to protect stored, intercepted, past information.
Okay, thank you. The next question is coming from Graham, one of our postdocs. Thank you very much for the talk. I would like to ask if the current COVID situation will have any tangible impact on the current or future investment in quantum technologies, in particular with regard to the job markets. Thank you.
Yeah, that's a very good question. It has had an impact. Because of lockdown and various other things and the difficulties of getting in and out of labs, it's meant that a lot of experimental programs have had currently of the order of a 6-month delay, roughly. So what we've been having to do with the UK program is to extend the funding of people that are in their final year of their PhDs to give them that additional time to finish. That then means a knock-on effect, because we would normally want to see those people moving into postdoctoral positions. At the moment, there's a job that there are many jobs and not enough candidates for it. And I think everybody will tell you the same story, that people are finding it quite difficult to recruit at the postdoc level. And in addition, industry is finding it really hard to recruit at the moment. So what COVID's done is boost a 6-month delay. What we can do to help is to provide extensions for the grant periods that have funded people. We have to be elastic in working out when our delivery points were going to be, but it does look like about a 6-month delay in things. In some areas, it's been quite rapid. Now, as some of you know, I'm a theoretician. It's really not affected us, except that we're getting rather tired of spending our day on Zoom calls all the time. But the experiments are the ones that have been hit hard. On the job market, I think what it's meant is that there's been a kind of dislocation of the normal hiring periods on that thing. But I think it will self-correct, providing people are tolerant enough and found ways of doing those studentship extensions, postdoc extensions to keep people going until they finish what they were doing.
Okay, thank you. And the next question is coming from John Gabriel Hartmann. Thank you for the talk. I was watching the European Quantum Flagship talks earlier today, and I was wondering about the extent of collaboration between EU and UK programs and whether the Brexit will affect it.
Yes, I was watching the same presentations this morning, and someone did ask exactly this question of a commissioner, and I sat forward waiting to hear the answer, and there wasn't one. For the currently funded programs that are funded by Horizon 2020, we have contributed to the European Union platform of funding on that one. So the UK will participate. So that means that in the ramp up projects for the flagship, we will continue. One of the programs is called Quantira. In fact, I chair the Quantira board, and those collaborative proof of concept projects will continue throughout Europe with UK participation. Beyond that, who knows? And I find this kind of distressing, you know, even though I do work for the UK government, my instinct always is to view science as open and international and with whom we want to collaborate. And I really hope that we will find a vehicle to do it. We've started to look at bilateral discussions, working out how to put resource in from our budget to enable this. So I mentioned that on Friday, we will be announcing a funded collaboration with Canada. We have already the project with Singapore. And last week, we had an interesting initial discussion with our colleagues in Germany on collaboration as well. But who knows? I think in terms of, you know, Brexit, we have left the European Union. So we have to find a mechanism through negotiation of joining, just as Israel and Switzerland join in the European Union programs. But we've yet to get an agreement in the long term.
Okay, thank you. And sorry, Peter, can I ask a quick question?
Yeah, of course you can.
Sorry, if you would ask to bet which hardware will first break 1,000 qubit barrier, what would be your answer?
I'm very fond of trapped ions. Okay.
1,000 trapped ions.
But the superconducting people are moving a bit faster. And looking at the way in which the if you like, the spectrum of things you're trying to address in trapped ions, that spectrum gets really crowded as the number of ions grows. And so one of the ways forward for trapped ions, for example, is to modularize it, to have a local processor with a reasonable number of quantum bits under control in a modular form, and then build quantum photonic links between them. And that's always been the platform that we've been trying to explore in the UK, so that the fastest transfer of entanglement between two different modules has been done by the Oxford group led by David Lucas, using basically entanglement swapping to actually generate that. So I could imagine progress being reasonable if you had a reasonable number of qubits in each module and then link them up photonically. Now, it's very easy for me to say that because I'm a theorist and I don't have to do it. But the people who do it have some confidence in it. So there's trapped ions. On the superconducting side, the big issue is with the noise. You know, those superconducting bits are quite noisy still. So understanding the noise platform on those things is really interesting. But just to give you an example, IBM came up with this concept called quantum volume, which tells you how much quantum work can you do with a certain number of qubits. And IBM had the record in August with their superconducting bits of a quantum volume of 64. IonQ, Chris Monroe's ion trap startup, 3 weeks ago announced a quantum volume of 4 million. I know we need to look at it closely. Is it real? What can you do with it, and so on? Honeywell have also produced a structure with a tremendous quantum volume. It's early days. I think I'd focus on it. And then here's my awful warning. Okay, we're looking at a 10-year journey. I've just said ion traps or superconducting. Someone will come up with a platform that I haven't poked, and we'll beat all of them, because I'm bound to be wrong. Okay, and it could be, for example, PsiQuantum's photonic platform. Who knows? That's why it's really important at this early stage to start looking at the scaling options of a number of platforms before you throw everything behind one.
Okay, thank you.
Ilya, so Peter, I know that you have another commitment coming up soon, so I will use my my position here to ask you one final question. You know, we mentioned at the very beginning that in South Africa we are also busy with our own a little bit more modest quantum technology roadmap and framework. Do you have some advice for us? Because, you know, our budget, if we are very lucky, it could be the same amount of money in a little bit weaker currency. Yeah. So that probably we can't think as big as you are thinking in the UK. Do you have any advice for us? Things that we could focus on, or things that we shouldn't touch because they're too risky, or I don't know.
Right. There are a number of things I can offer in terms of advice, and I'm fairly certain, knowing you all, that you're already doing it. Okay. The first thing is that a strategy cannot be imposed on an R&D community. It can evolve from them. So when you're evolving a roadmap and a strategy for forward use, it's really important to be inclusive and to start using what the US called town hall meetings, and what it's horizon scanning on opportunity space by bringing in as many of your communities as you possibly can to explore that. Now with COVID, it's difficult, but you know, IT works, so you can do it. And so don't impose with a few visionaries saying, do this. We could never have got that UK program together without having community meetings. I used to look after a Royal Society residential place called Chicheley Hall. And what we basically did is we took all of the people that we could identify with a quantum interest and basically lock them up in this place for 5 days while we explored who could do what difference would it make, and how much work does it need, how much resource, and who needed this stuff in the first place. So community meeting, I looking at, you know, I've actually been involved in advising a number of countries in the same way. We've been looking at a Singapore strategy, for example, for the Singapore government. We've been looking at the same thing in Australia on this. Local needs must dictate how you build your strategy, because, for example, it would be extremely foolish to say, I'm going to put all my eggs in this basket, and it could be, for example, topological quantum computing, and I'm going to take on Microsoft. Yeah. You just don't want to do that. Okay, so where your strengths are, yeah? So how would I do it? Community meetings, get people, and beware of the passionate advocate. The passionate advocate might be passionate, but might not have evidence behind them. So look for the evidence behind everything on in terms of next steps forward. You guys did a wonderful job already in quantum technology. I always use the South African securing of the World Cup stadia using quantum as an example of early adoption of something which was both great fun and was real. So the fact that you guys did this in Durban was terrific. Work out what you can do locally with the skill base you've got, and in particular, using the enthusiasm of your young people. I think it's great.
Okay, thank you very much. So I think we are more or less on the right track then.
That's what I said. Knowing you guys, I knew you were already doing it all. So, you know, using NITheP, for example, as a catalyst for these things, you've really got a bit of an ecosystem to do that. That would be great. And let me tell you, you've got friends all around the world who would be quite eager to act as your critical friends if you wanted. Many of us have had wonderful experiences coming to South Africa, and we'd love to help because we can see a tremendous intellectual capability there.
No, thank you very much. So that's probably now the right time to conclude this colloquium on this very positive note. So Peter, thank you so much for sharing with us your experience in setting up a quantum technology program in the UK. And also thank you very much for your encouragement and support on our own trajectory to set up a quantum technology ecosystem in this part of the world. And who knows, maybe soon we will be able to communicate via satellite in a quantum secure way.
That would be a wonderful thing.
Yeah, no, we are working on that. Yeah. So thank you very much for your time and for sharing with us.
Thank you for inviting me as well. Okay.
Thank you very much for accepting the invitation. Yeah, and I hope we will keep interacting very soon. Yeah, thank you very much.
I hope so too. Okay, bye, folks.
Yeah, thank you very much.
Bye-bye.
Bye-bye. Cheers. Bye-bye.